Okay, so here's a lecture for finding surface area using double integrals. In the textbook, this is section 15.5, if you're following along. So the idea, before we get into any work, what we're gonna do is I'm gonna look at the graph. Here's my surface in three-dimensional space, some function of x and y. It's over some region R. This is similar to all the other double integral stuff that we've done. I need to have some region in the xy plane that I'm integrating over. So the idea that we're going to do is to figure out what the surface area of this is, because this is curved. I'm going to look at each of these little rectangles that I break this up into to get an approximation. So if I look here, here's a rectangle in my region. That's going to correspond to this curved area, this little curved segment of my function, or my surface. Let's zooming in. Let's zoom in on this and see what we can do. So over this rectangle R here, I'm going to have some curved thing that's happening, right? So to do the surface area, what I'm going to do is I want to use some approximation for each of these over my domain, and then I'll add together all those approximations to come up with a formula that I can then take the limit to turn into the actual double integral, right? So I can't do much here with this curved surface. But what I can do is I can use the tangent plane to approximate what that surface is. So here, let's just assume we're using upper left corners. This tangent plane, if I take that little piece of tangent plane that would correspond to this domain down here, then if I add together the area of this, that would give me an approximation for what the surface area of that curved shape is. So then adding all those up, I'll get an approximation for the surface area over the region. And then we'll see that we can take a limit to as m and n go to infinity, because I have two different dimensions happening at the same time. That limit to infinity will give me the double integral. So I need to think back, like, okay, well, how do I find areas of parallelograms or areas of tangent planes? That makes me think back to what we did in chapter 12 at the very beginning of this course, is we talked about cross products. So there's two things about the cross product. One, so let's say that this is my A vector here that makes up this side, and this is my B vector. The cross product is going to be perpendicular to both of those, so it's going to come up off, right? But if I look at the magnitude of the cross product, that's going to tell me the area of the parallelogram. So if I'm able to write this length and this length, if I can find the two sides of that and write them as vectors and components with an I, J, and a K, then what I can do is find the magnitude of that cross product and use that to create my formula that's going to tell me what the surface area of this region or over this region is. Okay, so let's talk about how I'm going to come up with the A vector and the B vector. So looking at the components for the A and the B vector, what I'm going to do is I'm going to take these two vectors that are, so that's my B vector, that's my A vector. I'm going to go ahead and move those and put them down here at the origin so we can talk about them a little better. So what I want to notice is when I look at this A vector, it would be along this right here, along this region, or along this line, sorry. So that's for a set Y value. So that means that this A vector is in the XZ plane. So the components for A, I'm going to have some I component. I'm going to have 0 in the Y direction. And then I'll have some K component. If I look at B, B is here along this direction, right? B is going to be here in that direction. So what that is, that's in the YZ plane only. Let me label these axes real quick. That means here, that's in this YZ plane. So that's going to have 0 for an X component. So I'm going to have 0I plus some J plus some K. So let's see, how can I come up with what that X and Y component is? Here, if I'm looking at this as my X and this is my Z, it's going to be a line that goes off like that, right? This distance here, well, that's just however big this is. That's my delta X value. So here, I'm going to have delta X. I have no J component. For my K value, well, I have a tangent plane. So if we think back when we talked about partial derivatives, if I have some value here, if I take the partial derivative, f of x is going to tell me the direction that my slope or my rate of change in the x direction. And then this, the partial with respect to y, is going to tell me the direction or the rate of change, the slope, and my y direction for my y components, right? So here, this rate of change, I could think of this as my change in z over my change in x. So if I want to know what this z value is here, well, if I know what the rate of change is, and I know the distance of how far I'm doing that in the x distance in the x direction, these two things are going to cancel out, right? So this, my k component, this distance right here, and my z-axis, this is going to be whatever my partial derivative is times delta x. That's going to give me the value, what the change is, what my z value is. So here I'm going to write partial x delta x. So now, similarly for my b value, let me clean this up here. Actually, let's use this siren. If I look here, that distance across is going to be my delta y. That's just my distance across this rectangle. My height here, well, I know my fy, my partial derivative with respect to y. That tells me, well, for my change in z, what my change in y is. So if I multiply this by delta y, that's going to tell me delta z. That's what I want this. So here I'm going to use delta y, and this will be f of y, delta y. So that gives me the components that I'm using for my a and b vector. So I want to make sure that we're clear on where they're coming from, that for this a value, this is only this a vector for each of my rectangles is it's only taking account for changes in the xz plane, right? It's going to live somewhere here or parallel to this xz plane here. Because as I move across this into my different values for x, for different constants of y, my x value might change, but I'm always going to be in a plane that's parallel this way. So that means I'm going to have 0 j component. I have no change in my y direction, right? Same thing for b. When I'm looking at this region here, my tangent plane, my b value, that's going this way. So it's going to be somewhere either in the yz plane or parallel to that yz plane. So that's why I have a 0 for my x component here, okay? I just wanted to make sure that's clear. In the book, it doesn't really talk about where those things come from. They just throw those formulas out there and expect you to know them. So I wanted to try to explain where those formulas came from. Let me clean up a bit. Okay, so we said I want to look at the magnitude of this cross product. Now that I have the two vectors written in components, I can go ahead and do that cross product. Let me write it over here. So I, j, k. Good reminder how to do a cross product. This is delta x, that's a 0. It's my partial derivative with respect to x, delta x. For my b vector, I have a 0 for I, delta y, and then an f of y, delta y. So when I do first we'll do the cross product and then we'll do the magnitude of that vector. The first thing I'm gonna do, I'm gonna write my component first in the I direction, and then that's gonna eliminate these two things. So then I just wanna find the determinant of that 2 by 2 matrix that's left over. So if I look down the main diagonal, this is gonna give me 0. I'm gonna get minus partial of x, delta x, times delta y. Minus, let's look at my j component. I'm gonna write the 3 values vertical here because I'm running out of space. So if I look at my j component, that means I'm gonna not look at these entries, and I'm gonna not look at these entries. So I wanna take the determinant of that resulting 2 by 2 matrix. So I'm gonna get delta x times f, the partial y, delta y, minus 0, because of this 0 right here. So now I'm going to look at the component for the k. So I'm going to cover this up and I'm going to eliminate these 2 values. So I'm going to take the determinant of that remaining 2 by 2 matrix. And so that's delta x times delta y minus 0. What I want you to notice is when I write it out like this, all of these have a delta x, delta y, delta x, delta y, delta x, delta y. So I could, kind of looks like a common factor, I could take those out. And what did we say delta x, delta y was equal to? We said delta x times delta y. That's what we called delta A. That's just the area of each of these little tiny rectangles here, right? So let me say this vector A cross B that's equal to negative partial of f with respect to x I hat minus partial f with respect to y j hat plus k all times delta A. Now what I want to do is I need to find the magnitude of this. So remember, to find the magnitude, I need to take the square root of each component squared. So that's going to be partial x squared plus, this is going to turn into partial y squared plus, my component here is just 1. So that's 1. So I'm skipping a little step. All of these would have that delta A. So I'd have a delta A squared, delta A squared, delta A squared. I could factor that out, take the square root, and then that's going to become the part on the back. So let's see what happens with this. This right here so let me trace our steps again. We had this because this was the magnitude of the cross products. Those 2 vectors A and B, those were the 2 side lengths of our parallelogram that we're using to approximate this little part of the surface. Ultimately, what I want to do is I want to do that for every one of these, every one of my rectangles here in my region that I made. I want to make this approximation for every one of these little regions on my surface, okay? So this, to get the actual formula that I want, I'm going to say, well, I'm going to add together. Let me try that again. Let me clean up for 1 second here. Okay, so what I have, I took that formula that we just had written here and I rewrote it up here. It's the square root of partial with respect to x squared plus the partial with respect to y squared plus 1, all inside the square root times delta A. That's the area of one parallelogram. So what I need to do is, my notation, I just said partial f of x. We need to be a little more specific about where we're evaluating all of these, right? So really, each one of these is going to be partial f with respect to x evaluated at whatever that corner is, whatever that point is that we're picking for each rectangle, right? So that would be x ij comma y ij. Then I have that value squared plus, so now here, the second one, I'm gonna have to do the same thing. I'm gonna evaluate that partial derivative at that point that we're picking in the region. So that's gonna be partial y at the point xij comma yij squared plus 1 delta a. And what I'm going to do is I'm going to add this together as a double sum. So I know we started talking about vectors kind of in between when we went from here to get to this formula, right? Please don't confuse this ij, the indices for my summation, as the ij that we're talking about, the unit vectors in the direction of x and y. Okay, those are two totally different things. I know that the letters are the same. They represent different things. Just touch on that real quick. So this is telling me here, m, again, this m value is telling me how many of these x's, how many intervals I'm going to chalk this up into, right? So right now, I would have a 3 filled in up here. That should be an n. They're not the same variable. So I have 3. In my x direction, I have 3 different rows that I'm talking about. In my y value, that's this n. That's telling me how many intervals I'm going to break my y values into. Here I would have 1, 2, 3, 4, 5. Okay? And then for each point, I'm going to pick one point from each of those rectangles here. I'm going to find this value. I'm going to add it together. That gives us an approximation for the surface area. To get the actual surface area, I want these approximations. Each of these parallelograms needs to get smaller and smaller and smaller and smaller and smaller. The way that those get smaller is, well, I need to have more of them, right? So if I cut more of them this way and more of them this way, that's going to make this smaller, which means I'm going to have less error, right? It's going to be a better and better approximation. So I'm going to take this, the limit, as m and n go to infinity. What that's going to do is that turns this part right here, that gives me my double integral over the region. And then I have this formula. I'm going to rearrange terms just slightly, and this should look very familiar to you. So I have 1 plus, let's call this, well, this is really just partial z with respect to x squared. And then this one is partial z with respect to y squared. And that turns into dA. This looks a lot like our arc length formula that we talked about, right? If this was just one integral, and then I got rid of this part right here, it kind of looks like arc length. All we're doing is we're taking that, it's that same thing that we did, and I'm extending it now in one more dimension, right? So this is the surface area formula. What we're going to go ahead and do is I will put a couple examples up next. I'll make 2 different videos. So a couple more examples, I'll show you some examples of how to actually use this formula. Again, so if I look inside here, square roots inside of integrals, maybe not your funnest thing that you want to do. So we're going to try to come up with ways looking for polar. So if I have polar stuff, I might be able to simplify that a lot. Different ways I can do substitutions or manipulate things to deal with these not fun integrals. Cool. If you have questions, please post discussion board, send me an email. Let me know if you're still in the course doing stuff. It's weird because I'm having like no interaction with any of you. Not any of you, I take that back. There's a few people who are emailing me and letting me know how things are going. It's really weird though teaching a class and not having interactions with you guys. So if you guys have questions or you're hanging in there, things are going fine. Like it'd be great. I'd like to know if you said, hey, everything's golden. Cool. Okay, examples next.